Well, welcome everybody to the Minnesota Astronomical Society's Beginner Special Interest Group. I'm Suresh. I coordinate this group for the club. I think I've been doing this for about 4 years now. And we have a pretty exciting presentation today. Bob Kerr is going to present on the ABCs of stars. Let's stargaze. Just a little background on what he is going to present on. Here's his little synopsis. Did you know that you can see over 3,000 stars with your naked eyes? The smallest star is just a little bit bigger than Jupiter, and there's a star that's larger than the orbit of Saturn. The oldest stars are almost as old as the universe. Elsewhere we look, the universe is busy either making new stars or making stuff from old stars, like planets and us. So what's going on with all these stars? Spoiler alert, a lot. So join us, and let's get some of the star stuff figured out. So a little bit about Bob. Bob Kerr, he just told me that he's been a member for about 17 years. He's a pretty accomplished amateur astronomer in his own right. He's a coordinator for 3 groups within the Astronomical League. The one that I'm most familiar with that he does is the Globular Cluster group within the Astronomical League. And he also coordinates 2 other groups, or co-coordinates, I think, on at least one, on double stars, binocular double stars, and the other one is advanced binocular double stars. So the Astronomical League, just so you know, is an umbrella group for all the astronomy clubs in our country. I don't know how many member clubs there are. There's probably close to 100 or so. And the Astronomical League provides programs for observers of all levels. So if you're a real beginner, if you're an intermediate, or if you're an advanced, they've got a program for you. And these could be, using binoculars or using a telescope or just using your eyes sometimes. So, and they run the gamut from things as simple as, or as interesting as, the observations that Galileo made back in the early 1600s, all the way to really advanced lists for very difficult to see deep sky objects. So, let's see. Bob has presented to our club a few times already. I know for our beginner group, I believe this is his 3rd time. And I know that he's presented to the main group for our club at least a few times over the years. And he's just a very knowledgeable and a very good presenter. So with that, I'm going to pass it on to Bob. Everybody, this is Bob Kerr.
Well, thank you, Suresh. I'll try to live up to that billing. And thank you very much for inviting me to speak today.
One more thing. Before I forgot. I almost forgot.
Sorry.
Everybody, if you have a question, throw it into the chat. If you look at the icons on the top of your screen, you'll see a chat button. Just go in there and type it in, and I'll read it off so Bob can get it and he can respond. Okay, Bob. Sorry about that. Go ahead.
Oh, no problem. I just want to thank you, Suresh, for inviting me to do this today. It's the first virtual presentation that I've done. So in advance, I'm already saying, well, if something falls through the cracks, we're going to do the best we can to bail it out. But I appreciate the opportunity to present today. When Suresh invited me, he said, well, what would you like to talk about? And my default topics, as he was alluding to, are things that I'm most familiar with, the Globular Cluster program and double stars. I actually authored the double star programs, and that is my pet project. But he's very right in saying the Astronomical League has a lot to offer. And those of you who are members of MAS are automatically members of the Astronomical League. And the very capable Jerry Jones is your coordinator. So if there's a question that Suresh can't answer, I'm sure that Jerry could handle that for you. So I chose the topic of stars. I think it makes sense. As amateur astronomers, we spend a lot of time out at night looking between the stars, or using the stars to point to things like galaxies or nebula that we want to star hop to. But stars themselves, although they're most dramatic in the evening sky, we very infrequently think about looking at. Whether we look at them or not, they play such an important role in the universe that they should be at the front of our thoughts when we go out at night. So I don't want to spend a lot of time with this introduction. I hope you enjoy it. As Suresh suggests, please ask questions if you like. And as far as being a beginner, I'm not sure what that means. I don't know many of you, but I was a beginner twice. I was a beginner when I was in high school, when I actually was mentored and ground my first 6-inch mirror. And then I stepped away from the hobby for quite a while and came back. And actually at that point, I was a beginner again. And there were so many new things I had to learn. So I'd like to just take a minute and tell you how I became a member of MAS. This may resonate with some of you who are maybe retired as I am and or have time now to explore something you love or look into it. I happened to be looking through the newspaper one day and I saw an announcement that something called Astronomy Day was going to be held by an organization called the Minnesota Astronomical Society at Odin Observatory. And my daughter and son-in-law, being enthusiastic as they are, said, well, let's go check that out, Dad. So we did. We got in the car and went out. In the early 80s, I had purchased a Meade 8-inch Newtonian telescope. And this turned out to be the little telescope that could. I think it was a Christmas gift initially, and we spent a lot of time with it, but again, drifted away from it. And first it was in the garage, then it was living under the stairs. So it'd been quite a while. I decided I was going to get it out one night, and I couldn't get it to focus, and I was getting all frustrated. So I thought, I'm going to take it out to this astronomy deal thing and see if somebody out there can steer me in the right direction. Here we are in 2003 at Odin Observatory. My son-in-law just happened to have the camera at that time. And it was one of those cold, that's right, all astronomy days are cold and wet and damp, but this one was particularly so. So we got out there, and that's my telescope, and a group of very interested people. It's like, oh boy, somebody's here. Let's go over and greet them, which was great. This individual named Steve Emmert showed the most interest. I don't know if Steve is tuned in today or not, but he was there that day. And he said, well, let's have a look at this old timer. And I was hoping he was talking about the telescope and not me. So he did that. It was very helpful. And we were looking at this, and he said, I think I see your problem. And we looked even further into the telescope tube. And I don't know who this gentleman is behind Steve, but he also was helpful. If you recognize him, I don't anymore.
That's me.
Who? I don't. Who's saying that?
Don Gazdick.
Okay, Don. Sorry.
Don, you were very helpful, apparently.
Okay. I don't think even Steve would remember this, but it was a very important turn of events in my interest in getting back into astronomy. I can blame Steve for everything that's happened to me since then. So the secondary was a little bit loose, and he said, just a little bolt right here would tighten that up for you and everything would be great. So I was so impressed, not only with Steve, but with everything that I saw and experienced there. I said, well, I really need you guys. I think I do. And he said, well, you ought to join the MAS, Bob. And I think we signed up right there on the spot. And that kind of put me back on track again. This is my daughter off to the right, by the way. She's taking it all in, thinking finally something to occupy this man. So I went on with this little telescope. The first thing I did was to replace all the components of the optical tube except the mirror. This 8-inch mirror from Meade has been amazing. I've cleaned it a number of times, but it has never been recoated. I still have this telescope, but it's gone through some iterations. I painted the tube black. I like the stylish look of the white tube, but it's not practical for me. When it's dark out, I like to observe with two eyes open just to relieve the eye strain. And it's hard to do that when one eye is looking at a white tube. And also, I just think the dark adaptation is better with the black tube. So that's one change we made, and that's Losmandy mount that I had bought for the telescope. And then some years later, it got pressed into duty during the Venus transit. It's set up here with the filter just to use as an optical telescope. And it's been demoted to a celestron mount because the Losmandy mount is underneath our imaging rig that Mark, my son-in-law, was helping me with. And we had a good time doing that. I actually find that although I have astro buddies all over the country, it's always fun to do something with members of my family. And I urge all of you, whenever possible, if anyone in your family is remotely interested, get them out to this telescope and try to get them interested in sharing the hobby with you. My daughter and my son-in-law, as I say, have been very supportive. And down the corner is Queen Cassiopeia, Cassie, who gets in on the action when she isn't taking a nap in the chair. Of course, I could say the same thing for myself. All right, enough of that. Let's get to the topic at hand. At one time, stars were very much the focus of observational astronomy, along with solar system objects. And then we're kind of left in the backwaters with amateur astronomers as we have more fun looking at deep sky objects. Well, actually, this is probably a well-kept secret, but stars are also deep sky objects. So we use them as markers. We hop around them. But of course, none of us would exist if it weren't for stars. And if that's a little hard to process, we'll talk about that in a little bit. So please feel free to ask questions. As long as they're not too hard, I'll make every attempt to answer them. So I guess we'll start basically with, what is a star? Stars are actually nuclear furnaces that are balls of gas. It creates a kind of tug-of-war between the fusion that's burning the hydrogen that wants to expand out and get away with the force of gravity, which kind of pulls things back and makes a round shape. A round ball being the most efficient shape there is. It doesn't have corners. It's perfectly round. So our sun is actually classified as a dwarf star, and we'll be talking about sizes in a little bit. But the idea here is that when stars lead most of their lives are on what's called the main sequence, and for the most part, they're relatively stable. We'll talk about some exceptions to that. When we observe stars, there are a couple things to keep in mind. Excuse me here for a second. Mark, something's happened to the presentation. My slides are out of order. Can we reload this off the stick, Mark? I have to reload this. I don't know. Something's happened to the sequence of this.
So, guys, why don't we take a pause for like 5 minutes?
Yeah, sorry, guys. We'll
something back at 1:20. That's like 6 minutes from now. Okay. All right, everybody. It's 1:20. Boss, please turn on the recording again. Thank you.
Done.
Okay, I don't know. I apologize. I don't know how my slides got out of order on me somehow, and we're planning on taking a little intermission in a bit, and I'll try to get those back in order again.
Ask Suresh if he wants to take some. There's several questions up here now.
Yeah, did you want me to see if there's any questions here? So Mark asked, are all stars hydrogen-based?
The composition of stars essentially represents the composition of the universe in general, which is mainly hydrogen-based. Hydrogen, helium, and a mixture of higher-order elements. That is the newer generation of stars. Early stars were almost 100% helium. But the stars are burning helium. Does that answer the question?
Mm-hmm.
Okay.
And then a second question from Lewis is, so where do you focus your telescope to get the best action? I'm not sure what he's asking about there.
Okay, Lewis, just stay tuned. We'll be covering all of that for you, I promise.
All right. Anybody else have a question for right now, or should we continue?
Should we get started? Yes.
Okay, Bob, it's all yours.
All right. Well, as far as we can tell, there may be about 400 billion stars in the Milky Way galaxy alone, and that's only one galaxy of billions, as you know. And both ground-based and orbiting telescopes, most recently the Gaia mission, have done much to further our understanding about stellar evolution, although we may not ever be completely certain about the estimates of stars in the Milky Way. We can only imagine the effect that the night had on the ancient people before we had Netflix and things like that in the evening. They spent easily half their lives under dark skies. And they guessed, they looked at the heavens, they must have been fascinated and maybe a little bit fearful of what they were seeing because they hadn't any idea of what was there. But clearly the stars were there. They wondered what they meant. And ever since then, and we're talking, we don't really know the first person that looked up and said, what's that light in the sky? That'd be interesting to know that, but we don't know that. So for millennia, we've looked up and not known what those lights in the sky were. And actually, until very recently, in terms of human history, we did not know what those lights in the skies are. But thinkers and philosophers and astronomers throughout the ages have asked that question. What are stars? They're immense nuclear furnaces and sustain themselves by most of their lives converting hydrogen into helium. And in the process, the stars emit great quantities of energy in the form of heat and radiation, which, including photons, which our eyes detect and say, aha, there's light. So I kind of got onto this. So this is the balance of nuclear fusion. Wants to push the star outwards. It's burning helium at a ferocious rate, and that wants to escape. The force of gravity, which is holding the star together to begin with, and was very instrumental in the birth of the stars in general, we'll talk about that a little later, is saying, no, you're not. We're going to just stay right where we are. And the effect is an equilibrium, with the energy of the nuclear furnace wanting to push gases outward to escape with gravity holding it in. And all stars are fundamentally based on that same principle. As stars age, things seem to change, and we'll talk a little bit about what happens when stars age and when stars die. But there's a tug-of-war balance continuing, but it maintains, for the most part, the equilibrium of the stars. This is kind of a pie chart using a star as the pie. Someone asked about hydrogen or helium. The universe is composed mostly of hydrogen, gas, and dust. So the stars also, as they're being born, take on the gas and dust of the molecular cloud where they're being born. So the mixture is a little bit different, and that has a lot to do with the brightness of the stars, their size, and their mass. But at least in the case of the sun, we have mainly a hydrogen-burning sun, which is about halfway through its supply of hydrogen, and is going to be going strong for quite some time. In many ways, our star is an average star, but when you look, and we'll be talking about stars in general, it also is different in many ways. So what you're seeing on this little pie chart is really the hydrogen, helium, and then this other elements, and these are higher order elements that were created in previous generations of stars. These did not originate in our sun, but the sun inherited these when it was born in the molecular cloud. The first thing we notice when we go outside is, well, other than is it cloudy or not, is that some stars are brighter than others. In the sky that we have at this time of year, we see the constellations Orion, Canis Major, Gemini, and Taurus, which are reflected in this little slide. And we see a great many bright stars at this time of year. So the brightness of the stars is we express as a magnitude. How bright is the star means what's the magnitude of the star. In general, magnitudes are expressed as absolute magnitude and apparent magnitude. I don't mean to get too esoteric here. Always ask if you need clarification. These are just really kind of basic concepts, but absolute magnitude is really how bright is the star really? Because we're seeing at a distance. So how bright is the star really? And astronomers have come up with a hypothetical distance of putting every star in the night sky at about 32 light years away and saying if all of the stars in the night sky were 32 light years away, how bright would they be? That's going to be the absolute magnitude of the stars. Well, that's interesting, but that doesn't do us a lot of good. What's interesting to us is their apparent magnitude. That means when we're standing at the end of our driveway or the observing field at Onan or wherever, is how bright does that star appear to me? It's almost irrelevant as to how bright it actually is. How bright does it appear to me? So that we call apparent magnitude. How does it appear to be? And this is based on a numeric scale thousands of years old, credited to a Greek mathematician by the name of Hipparchus, who has done a great deal. He's the father of trigonometry. I don't know whether he's the father of astronomy. That honor probably falls to Ptolemy, who we'll get to in just a second. But Hipparchus was a bright lad, and he said, I'm going to come up with a way of defining brightness in stars. I'm going to come up with a numeric scale. The brightest star I can see, and let's just assume that was Sirius, because he saw Sirius. So that's going to be a 1. And the faintest star that I see, and for all he knew, the faintest star there is, he had no idea of the other stars. They're only the stars you could see, were only the stars that existed for them, is going to be 6, which still remains what we call the limit of human vision. You know, the pupil of your eye isn't very large. It's only, at its largest, is only about 1/4 of an inch. So it's no wonder we need telescopes of 6, 7, 8, 10, 20 inches in diameter to gather enough light to see these other stars. So Hipparchus said, I'm going to make up a scale, and I'm going to rate every star between 1 and 6, and that will be their apparent magnitude. So what do you suppose happened? Well, somebody came along and invented the telescope. I guess we're going to credit Galileo not with the invention of the telescope, but with what? Turning the telescope up into the sky and saying, oh my gosh, there are far more stars here than I ever imagined there could be. So, well, right away we had to modify Hipparchus's scale and say, well, we're going to have to keep numbering. Stars that I can see with my naked eye are going to be called 6. And when we amateur astronomers say we want to get under clear dark skies, which we certainly have up north at LLCC, we can see all the way to the limits of our individual eyes. As eyes age, and you can take me at my word for this, you can't see as much as you used to. A new set of eyes, a young set of eyes, pretty much is going to see, all things being equal, going to see better because their pupils are larger and remain larger. The lenses aren't yellowed. So the older you get, the less you can see. So anyway, with optical aid, we go all the way up to a 10, and we go much farther than that, of course. Yeah, a good pair of binoculars will take you easy to 10th magnitude. Beyond that, we need a telescope. So we thought, okay, now we're really in business. And then again, somebody came along and said, wait a minute. We're not quite there yet. What we need to do is account for things that are really bright. So we rejiggered the magnitude scale and say, well, we can have stars brighter than first magnitude. And the way we did that was to go into negative numbers, as you can see here. So in the bottom half, we're going brighter to dimmer, and on the top, we're going brighter to dimmer, but the numbers go in reverse order. So we do have stars at -1, -2. Let me give you an example here. We go to Jupiter at basically -3rd magnitude, which is, you know how bright Jupiter is in the sky. And Venus is almost 5, and you know how bright that is. Venus is the brightest object in the sky other than the moon and the sun, which the sun being almost 27th magnitude, -27, which is really bright, obviously. There's nothing brighter in the sky than the sun. Also notice that we've also gone to tenths and hundredths. So we've really diced up these magnitudes to give us a lot of latitude in between each of the magnitude scales. Practiced human eyes can tell the difference, but basically now we're talking about instrumental astronomy that we come up with these kinds of scales. I just want to point out that when you're looking at printed star charts, we use the larger the circle, the brighter the star. Doesn't mean they're bigger. These aren't disks. We don't see stars as disks. We see them as points of light. So whenever you see these maps like this, you can tell what stars are bright and which ones aren't. I know you don't rely totally on the star charts in astronomy or sky and telescope, but you look at those charts and they're obviously designed for people that either don't have dark skies or don't have access to telescopes. The charts in Astronomy magazine go to 5th magnitude. And for reasons best known only to the editors of Sky and Telescope, there's only go to 4th magnitude. And we'll talk a little bit about 4th magnitude stars coming up here. There is a difference, a significant difference between apparent magnitude and absolute magnitude. And in fact, it tips greatly in favor of absolute magnitude. I've got a few charts here that I put together. I don't know what kind of devices you're looking at this on. Anybody with a tablet or a laptop will do fine. I don't know if you're looking at this on a smartphone, if it's going to work for you, but we'll just go through this quickly anyway. I've come up with this scale that shows across the top the apparent magnitude, which is what we see when we go out and look up at night. The absolute magnitude, which is the scale read at 32 light years. And just for comparison's sake, the distance away they are, where they really are. So let's look first at Sirius, which as we said, is the brightest star in our sky. Sirius isn't that far away. It's only 8 light years, which means that the absolute magnitude and the apparent magnitude are almost one and the same, because that's closer to us than 32 light years. So we'll go on down here to Canopus, which we don't see. That's in the southern hemisphere, but it is the second brightest star in the sky. And look at Canopus. It's out there at a whopping 300 light years, and it weighs in at a magnitude -5. So at 32 light years, that would be a lot more bright than Sirius. And this is how we tend to equalize, what we realize about what these stars really are versus what we see. Let's drop down here to Rigel, Procyon, and Betelgeuse. Rigel and Betelgeuse are quite distant. They sit out in the Orion arm of one of the outer spiral arms. And they both weigh in as being pretty bright stars. And they're, of course, bright in the night sky as well. But if you compare the three sitting there, Procyon is relatively close. And if it weren't, it wouldn't at 2.6 magnitude. It wouldn't even come close to matching the other stars in brightness. Let's drop down and look at Antares, which is in Scorpius, which is a summertime constellation. I don't want to make the assumption that you're all familiar with these brighter stars. Possibly you are, or possibly you'll make a note and check them out the next time they're in the sky. But Antares is a whopping 600 light years and a whopping -5 magnitude, and it's pretty far down the list. It's 1.06 magnitude. But the all-time champion has got to be Deneb. Look at that. It's the brightest star on our scale, and it's 3,200 light years away. That is a whoppingly bright star. Deneb sits in the tail of Cygnus, and I think it's in Arabic, it means tail of the hen. So we tend to look at the Northern Cross a lot. We'll be talking a little bit about the Beta star, which is a favorite double star, Alberio, which sits up at the opposite end. So that's the story on absolute and apparent magnitudes. It's basically what you see is not necessarily what you're going to get, because it's what the apparent magnitude is of these stars that really matters to us as amateur astronomers. The other really important factor is called limiting magnitude. And if you don't know what that means, you'll see when we get into the example of it. But it's really absolute magnitude and apparent magnitude are factors that are kind of out of our control. Limiting magnitude is what we see when we stand in our backyard and look up. Limiting magnitude is the effect of our local environment and situation on what we can see in the night sky. I have just a rough, actually kind of a poor example of this, because this doesn't really do justice to what the urban view looks like, but you get the idea. Kind of like looking through a haze or a fog. I'm assuming that the rural is clear dark skies, and we can see all the way to 6 magnitude. Now, this is an image, so we're seeing stars fainter than 6 magnitude. But under a clear dark sky, we can see to 6 magnitude. I don't know about you and where you live, but I have a limiting magnitude of 4 at my house, which means that I can't see a star with my naked eye that's dimmer than 4th magnitude. There are a number of ways when we go out at night, we can check this out. And there are meters, there's electronic meters that let you do that. But I found it handy to use the stars in various constellations as markers. This is, of course, the Little Dipper in... I'll get to the question in just a second. In Ursa Minor. And it's a dim constellation to begin with, and as you know, that the tip of this is actually the bear's tail that we're looking at here, is Polaris, the North Star. Here are the various absolute magnitudes of these stars, and apparent magnitudes of these stars. We can see they run the gamut from Polaris at 2 to Eta at 5. So if we use this as a scale to determine limiting magnitude, if we go out at night and all we can see is Polaris, we're in rough shape. And this is a circumpolar constellation, meaning that it's pretty high up in the sky, except when it's, when is it? Circumpolar, December through March, it's pretty low, which means it's dangling back way down kind of onto the northern horizon, and it might be affected by sky scum or whatever. But to know this, and if you locate the Little Dipper, you can kind of tell by the stars you're seeing there what you might expect in general. If you can see all of them, you're in really good shape. The other one I like is the Great Square of Pegasus, which of course sets about the first week, or rises about the first week in August. It's not as available as the Little Dipper. Within the Great Square, we have at the corners all stars that are second magnitude, even though we got, 0.1/10, 4/10, 5/10, and 8/10. They're all referred to as second magnitude stars, but we've got one that's closer to 3 third magnitude. So again, if we look up and we can see all of these, we know at least we're seeing the third magnitude. On the other hand, inside the Great Square, and this is the constellation Pegasus, the winged horse, and this is a kind of the tail end of Andromeda. They share the alpha star here. They argue about that a lot, but they share that. That's not uncommon in constellations. But within that, we start seeing dimmer stars. And there are 4 stars there in particular, in the range of 4th to 5th magnitude. And if we're seeing those again, we know we're in pretty good shape for the observing we're going to do. This is where we're missing those slides. All right, this is where the bug appeared, and I've lost some slides in here. I'm going to try to recapture them, but let me deal with the question that came up. Who had a question for me?
So Ashwin Rawat asked, do we know the absolute magnitude of the sun?
That's a good question. Because the sun is so close, it's got to be close to that minus 27. I don't know the answer to that. I see Dave is hanging out. Do you have an idea, Dave? It's
4.83, Bob, positive. So that's the absolute magnitude. The apparent magnitude, like you said, is minus 27.
Okay, good to know. Thanks for asking that question.
Bob, one other question on a similar topic on absolute magnitude. The 32.6 light year distance for absolute magnitude, how did they come up with that? Do you know?
I think it's a scale that seemed to make sense to them. They don't want to get too close. I think the idea is up to about 32 light years. There isn't that much difference between the apparent and the absolute. I don't know for sure, but that would be my guess, Suresh.
So as I recall, it has to do with parallax. So
no, it doesn't have anything to do with it.
Actually, it does. It's 10 parsecs, and it's the distance where the parallax would be, I think, 1 degree.
1 arc second.
One arc second. And it's 10 parsecs.
I don't know what relationship that has, though, with determining the magnitude, David. What would that be?
Well,
so if you measure a position of a star when it's 90 degrees from the sun in the evening sky, and then come back 6 months later and measure the position of the star when it's 90 degrees from the sun in the morning sky, it's that distance, that parallax, that angle difference is how they measure that. And it comes out to about 32.6 light years as to if a star is out that far, it will seem to have moved 1 arc second from either of those two when you measure those two distances.
Okay. Any other questions?
I'm not sure what Matt is asking here, Bob, but Matt Dunham is asking what is the crossover magnitude number between the two scales?
I'm not understanding the question. What
I mean by that is it's kind of like Fahrenheit and centigrade or something. What two temperatures are the same on the scale? At what point do the two magnitudes cross, or what star is considered the same magnitude on both scales? Is there such a thing?
Well, I think we saw that Sirius was as close a match as we could find.
Oh, I saw those as plus and minus.
I'd have to go back and find that slide, but there isn't much difference between the apparent and the absolute magnitude on Sirius. I think there was just a tenth or so.
find a star that's 10 parsecs away, and that would have the same absolute magnitude and apparent magnitude.
Makes sense. Thanks.
Okay. So I'm going to go to my next slide, and I apologize because somehow the PowerPoint acted up on me, and I lost some slides. They're up closer to the start. So we're going to just move on. The next slide talks about the size relationships of stars, kind of in relation to what they really are. And excuse me, I'm going to just pop this up. Oh my gosh, lost a lot of content. I apologize for showing all this stuff, but I don't want to. How do I find this?
Bob, should we take another 5-minute break?
Move on. Just go through where you stopped.
Why don't we just take a few minutes here, guys? Let's circle back in 5 minutes.
Well, let's pick it up here.
Okay, never mind.
Yeah, I apologize. So we're talking about, at this point, the constellations. And we're teed up on asterism right now. You know, guys, I really apologize. Suresh, I apologize to you wholeheartedly. I do not know how I got these slides messed up.
Why don't we take a few minutes here?
If we could take a break, Mark and I will try to get these back in order.
Why don't we circle back at the top of the hour at 2 o'clock? That should give you time, right?
Yeah, thank you.
Okay, we'll circle back at 2 o'clock, everybody. Looks like Bob's back on, so we're going to get started here. Go ahead, Bob.
Yeah, I totally apologize. We got some kind of a hit here that messed up the PowerPoint slides, and I hope that we can proceed from this point on. I really apologize to you.
No worries, Bob. This stuff happens.
So we're at the point now of the second thing we're going to talk about is some stars are brighter than others. And we kind of reviewed why that was because of the distances and so forth. So what we're going to talk about now is stars that appear to be in patterns. And of course, these patterns we know to be constellations, from the Latin meaning set of stars. You know, it's natural that the human eye sees patterns in things, whether it's something, you know, stupid like a pattern in wallpaper or carpet or whatever, or even fluffy clouds in the skies. I had to laugh. Last summer, I saw Fred Flintstone in the sky. Say hi, Fred. So what patterns do you see here? The eye wants to make patterns, and what we see here are the stars of Orion, Lepus, and Canis Major. You know, the hazy band we see overhead are billions of stars. Now we also see dark areas, which is the nebula at the edge of between us and the core of the galaxy. But the Via Lactea is what the Greeks called it, and that means Milky Way. So in the stillness of the night, we are looking essentially at the same sky the ancients looked at, and they developed their mythologies around what they saw, and they started putting their gods, heroes, and monsters in the sky and building their mythology stories around them. And from these ancient imaginings through the ages, constellations have been added, constellations have been subtracted, and what we have handed down to us are constellation stories, somewhat lost in time, but are really coming out of the Middle East and Greek mythology. So we look up at the night sky, and do we see the dreadful scorpion that killed Orion in the night sky? Well, it's there. And it's an ancient constellation dating all the way back to the Babylonians. I'm not an authority on constellations. I am kind of a buff on old star charts and star maps, which are all about constellations, but the stories themselves, I think, are interesting for amateur astronomers to know about. They're not core to our appreciation of astronomy, but they do broaden us, and sometimes they make for interesting stories at star parties. But the good news is that within MAS, we have two experts. I think Dave is with us, and Jonathan Papelli. I'm not sure I know that I'm pronouncing that correctly, and I apologize to Jonathan, but maybe because I'm promoting his book, he'll cut me some slack. But it's wonderful that we have that kind of expertise in the club, and I know they share those stories with us. So we'll just go through some of the more interesting constellations that we know. Ursa Major contains the Big Dipper. We've got the strongman Hercules, who maybe you never knew this, but he's actually upside down. He's also called Hercules the Kneeler. And I think you can see in that string of stars that are up there on the right-hand side is where he may be kneeling down. But Hercules and Pegasus, the winged horse, for reasons that I don't know, are flying upside down in the night sky. Leo the Lion is a popular target, particularly because of the galaxies that are close by. Pegasus, the winged horse here, whoever the artist was, have him right side up, and I'm sure Pegasus appreciated being right side up for a while. Cassiopeia, the queen, or the lady in the chair, sometimes is a W and sometimes is an M, depending on where it is in the sky. She's circumpolar, which means she circles, and she's always in the night sky, and sometimes she's upside down, and sometimes she isn't, and I don't really think she cares. Perseus the hero is one of my favorite constellations. We'll talk a little bit about Perseus later. And then, of course, we keep coming back to the constellation of Orion, which is a fabulous constellation that always catches our eye, particularly at this time of year. When we look at the winter sky, we're actually looking away from the center of the galaxy into the Orion spur, which the sun occupies. And for the most part, these stars are much closer to us than the summer stars, which are farther away. And we see some familiar asterisms. An asterism is a signpost. For us, we look at asterisms in hopes of using them as stepping stones to find what we're really looking for. And an asterism isn't a constellation per se, but of course they're all parts of constellations. But they're familiar patterns and shapes that help us find our way around the night sky. The circlet is one of the dimmer asterisms. Of course, probably the most famous asterism is the Big Dipper. The Keystone of Orion is another good one. We use that a lot when we're looking for the globular cluster M13, which sits out there at the side. Another one is the Kite of Boötes, which is another important constellation and also has the bright star Arcturus in it. The stars of Cassiopeia and Triangulum kind of speak for themselves. We were talking about that as the M and the W, and obviously there we have a triangle. Of course, we have Cygnus the Swan, which has the magnificent Northern Cross embedded in it. We have the backward question mark of Leo the Lion. We have the wonderful teapot of Sagittarius, the Archer in the low southern sky. And of course, if you're not familiar with the asterism per se, you're probably familiar with the wealth of deep sky objects around it. When we look at Sagittarius, right off the end of this, the spout of the teapot, we are actually looking toward the center of the galaxy. So there's a lot going on in the Sagittarius Scorpius area of the sky. And then I'll throw in again the square of Pegasus, which are very recognizable. Let me just get a shot of water here. So another look at the wonderful winter sky. Where did all this start? Well, we talked a little bit earlier about Hipparchus and what he had to contribute. He was perhaps one of the first we would recognize as trying to actually make sense out of the night sky in terms of the stars and patterns. Sometime later, Claudius Ptolemy came along and really kind of put things together, researching not only the works of Hipparchus and some of the earlier Greek astronomers, as well as tapping into what came out of Babylonia and Mesopotamia, kind of tying this together. And at this point, we were kind of starting to take a look at the sky and maybe as something other than just its mythological ramifications. A number of important works predate Ptolemy by many hundreds of years, but his personal observations of the night sky and compiling these things together in a work of his called a treatise included celestial observations and theories on what was going on in the night sky. We see him holding a cross staff, which was used to measure stars, I believe, above the horizon. His work was finally published as late as 1515 in the Almagest, which was a catalog of over 1,000 stars and their positions that, for the most part, were the works of Hipparchus. He did some observing on his own and largely started moving the idea of the stars and the stars within the constellations to represent actual arrangements in the night sky. You have to understand that much as Hipparchus tried, he was not dealing with precision instruments. So his measurements were not as precise as later measurements, but considering this is all done naked eye, he'd done a pretty good job. A couple of years ago, I was lucky enough to go down and spend some time at the Linda Hall Library in Kansas City, which is an archive of over 500,000 pieces of astronomy, including books and charts. And you can go actually in there by appointment and look through these things yourself. You have a curator there with you. I don't know what they're doing for COVID. Maybe they have the whole place shut down, but their funding depends on outreach, and they are there, and the citizens of Kansas City and the local club in Kansas City spends quite a bit of time there. And I was fortunate to spend about 4 days there. I was working on another project, but I also got a chance to handle some of Herschel's notebooks, works by Newton, Galileo. I was there actually to look at star charts, but it was like a kid in a candy store. I didn't know what to look at first. But I did look through the first edition of the Almagest, and I took some photos of it. And what he's done is to compile this catalog based on the measurements of Hipparchus, which were actually made about 3 centuries early. And he ordered the stars in the constellation according to their brightness. Now, you can't read these. I can't read. I just took these with my phone. You can't read these, but they're all the bright stars within each constellation. And he's ranked them according to their apparent magnitude, of course. So he had tried to organize the heavens, and he created 48 constellations based on the constellation myths of the time. We now know that there are 88 recognized constellations, and of course, that includes the constellations of the southern hemisphere, which, although Ptolemy recognized that the world was round, he had no idea of what was down below the southern hemisphere. We did get a accurate accounting sometime later on that, but so 88 constellations is what we have. And at one time, I think there were up to 106 constellations, and thankfully those got thinned out. But he had no illustrations of the constellations. He only had the descriptions of the constellations. The stars, interestingly enough, did not have numbers, did not have proper names the way they do now. So each of the stars, the major stars, were based on the star's position in the imaginary constellation. So you look up at the night sky and you find Aldebaran because it's the reddish one in the southern eye. So you have to know enough about the arrangement of the stars in the constellation, know what that would be. In Hercules, it's the head of the kneeling one, or in the case of Pegasus, Enif is the nose of the steed and the tail of the hen and so forth. So that was state of the art for stellar recognition in Ptolemy's day. And I should say, by the time this was printed, we knew a lot better than that. But this is just a reprint of what he did. This is not by any means current to what was known in 1515. His measurements were crude, but they did become a standard reference for 1,000 years. And interestingly enough, until Tycho Brahe finally released his observations, which were much more precise, and then printed by Johannes Kepler in 1600, all of the work previous to that in trying to organize the night sky were based on these inaccurate and old numbers that came from Ptolemy. Now, at the same time, in the 2nd century, the Hyginus, the Roman writer, wrote a book called the Politicon Astronomicon, and these were the first attempts to actually take the constellation myths and put them into a set of stories and develop around them illustrations of what these constellations might look like. And these were early attempts to illustrate these constellations. And I think if I didn't have titles on them, you'd pretty much know what they were based on these illustrations. They don't look like the constellation figures we're familiar with. I mean, maybe Boötes you wouldn't, but certainly Corona, the Northern Crown, and Taurus, the Bull, and the two figures would stand for Gemini, the twins. So he was at least getting off to a right start. Now, if we look at the way the constellation figures are illustrated, we'll see that the stars are not in any precise order at all. They're used mainly to adorn the constellations and kind of be embellishments. There's no real effort to position them as they would be in the sky. So the emphasis here was on the constellation stories and just kind of sprinkle a few stars. Let's put one at each of the knees and one kind of on the hair and some in the club. But this did have the essence of Orion. We know he carries a club in some versions, and he has in some versions, he does have like a wolf's pelt or something in his hand. And I should say at this point that the figures we see here from portrayed here, there is no official illustration of a constellation. I mean, there are official positions of the stars. We don't change that. You'll see variations on how the stick figures are created. They're different in Astronomy magazine than they are in Sky and Telescope. But if you're going to base the constellation figure on stars, then this doesn't work out. In 1540, Alessandro Piccolomini came up with an approach that should look something familiar. There's certainly no constellation figures, but there is an attempt to position the stars accurately. And again, these are based on Ptolemy's catalog. And to a certain extent, he was ahead of his time. He actually used larger stars to mean brighter stars, and each of these stars had a letter. Now, these aren't the Greek letters we've come to use now, alpha, beta, so forth. But he was on the right track. And then after that, we kind of went back to some of our earlier depictions. Next, we have it's the seminal gold standard star atlas, the Uranometria of Johann Bayer. He was a lawyer, by the way. He didn't do any of his own observations. But he did have access to the 1600 catalog of Tycho Brahe. So his star positions were much more accurate than anything previous. These were very fine brass plate engravings, and it really set the standards for all of the catalogs that were to follow. Surely it had its flaws, but he also, by this time, was able to incorporate 12 of the southern constellations made by some of the explorers that got south of the equator. So let's talk about some of the real pioneering work that Bayer did in his star charts. His most brilliant innovation, even though we've probably forgotten his star charts, was the way he identified the stars themselves. Up until the time of Bayer, we were still going with random numbers or definitions like star on the left shoulder of the giant. He actually came along and said, well, gosh, why don't we just letter these? But I'm going to use Greek letters because, after all, these are Greek constellations. So we still use these designations today, actually. And here we see how that works out. Based on the Greek alphabet, from alpha to omega is the way the alphabet runs. And I guess we're more familiar with that because we started naming hurricanes using the Bayer designations or the Greek alphabet. But I'm sure that some of you are more or less familiar with the Greek alphabet. And I'm afraid to say, as amateur astronomers, we really got to kind of learn this stuff, particularly those that identify the brighter stars, because in a perfect world, the brighter stars are the ones closer to the beginning of the alphabet, like alpha, beta, gamma, delta, epsilon, and so forth. Although you're going to run across references to all of them at some point in time, and these kinds of little charts, like I've got here in the lower left-hand corner, are quite common, and you might want to just grab one and have it tucked away with your star charts. So anyway, we have Bayer to thank for the Greek alphabet designation of the brightest stars in the constellation. After he ran out of the Greek alphabet, he then went to Roman letters. But most of the things you're going to run across, the brightest star in a constellation is alpha. The second brightest is beta, and so forth. There are interesting exceptions to that. But it's only because these stars were probably fairly close in magnitude and they were using their naked eye. Keep in mind that his Bayer's constellation of star charts of 1603 predated the telescope. These are still all naked eye observations. So we're not seeing a lot of stars in his catalog because he was only dealing with the stars really identified by Ptolemy. So Bayer is generally credited with the first gold standard catalog and the one that was first most seriously directed towards Sirius cataloging of the stars and their brightnesses and their positions. The next generation I'm going to jump to is quite a while down the road, and there's some intermediate catalogs between Bayer and John Flamsteed. But John Flamsteed catalog is noted as probably the finest catalog to come along in terms of its completeness and accuracy. It was also huge, huge. Maybe it gets an idea about my photo here based on some of these that are in the background, but this is a huge catalog. I can't see lugging that out to my telescope every night and using it as a reference. I do want to say one more word about the catalog here of Johann Bayer. When I told you I had a chance to look through these, and it was so quick, but I was looking through its pages, and I was looking from a catalog that was printed in 1603, and I'm just serendipitously paging through, looking at various owners had made notes in very fine, I don't know how people wrote that small in those days, but very small notes in this catalog. And one was a page that showed Pisces, and it was from, I think, 1849, and somebody had noted the position of Uranus on that catalog in 1849. That catalog, over 200 years, it was still being used. And that's amazing. In our disposable society, the catalog that old, and actually by that time that dated, was still being used for tracking the planetary motions. Anyway, John Flamsteed was the Astronomer Royal. He was the first Astronomer Royal in Great Britain. And he was tasked, he was in charge of the first Royal Observatory, which wasn't well equipped. And John put a lot of his money into upgrading it personally. And he undertook a very thorough and comprehensive approach to cataloging the stars. He was going to finally do it right. And he made a significant contribution to the advancement of stellar designations, but more on that in a minute. William Herschel used Flamsteed's catalogs and charts. In fact, we'll talk about Flamsteed numbers in a while, but because he didn't actually publish numbers in this catalog, I shouldn't say catalog, on his star charts, his sister, William's sister Carolyn hand-printed all of Flamsteed numbers on the pages of the Flamsteed catalog so his brother would have access to them. One of the things that he wanted to do was to correct the orientation of the constellation figures. Kind of bugged him that Bayer had breached constellation lore etiquette by showing us the backs of a couple of the constellations, since Ptolemy had gone to great effort to say this is this Betelgeuse is the star in the right shoulder of the giant, and then the Bayer turned around and put it in the left shoulder of the giant. That kind of bugged John Flamsteed. So when he redid his catalog, he turned the constellation figure around so that would be right. He spent 40 years cataloging these almost 3,000 stars. And he had just a little working catalog that he would number these stars as he went through, only for his personal use. And he had very accurate measurements, and everyone, including Isaac Newton and contemporary astronomers, wanted access to these measurements, and they pushed him to publish these. And he wouldn't do it until he had checked them and double-checked them and gone over them any number of times. So some of his first work was pirated away from him by Isaac Newton and John Halley and published and became inadvertently known as Flamsteed numbers, although he never used them on his catalogs, he never used them on his sky charts. But you can see here I've circled stars that have Flamsteed numbers next to them. Some of these actually have lines through them showing that in the early catalogs, that used to be the designation for double stars. But any where you see a number like that in a chart, you can thank John Flamsteed for those numbers. Actually, you could say thank the people that stole them from him for those numbers, because that's how they got into circulation. He never intended to use numbers in his catalogs or his atlas, and they were both published after his death.
Hey, Bob, just real quick, a question. Those Flamsteed numbers, aren't they largely in order of brightness, or wasn't that their intent?
You're on the right track, but not exactly. I was going to cover that somewhere, but actually, this is where I'm going to cover it. The idea is that they run sequentially west to east. As you can see here, I've circled a 5 and 6 in Leo, and at the top left is 92 and 91. So the sequence is west to east, which is a progression of the way the constellations move through the night sky. Even Alpha Leo has a Flamsteed number. Flamsteed has numbered all of the naked eye stars. So any star that has a common name like Arcturus or an alpha or a beta designation also underneath it all also carries a Flamsteed number. So stars can have common names, they can have Bayer numbers, they can have Flamsteed numbers, and on and on. So I don't know of an area of study that has more different names for the same thing than astronomy does for its stars. That answers your question, Suresh? Okay.
Yeah, thank you, Bob. Does anybody else, we have a pause here, does anybody else have a question? All right, all yours.
So I just wanted to point out here the corrected view of the figure of Orion here. The star in the right shoulder finally got it right, and somewhere Ptolemy was smiling. Now, what happened eventually with these star charts, as time went on, we got more and more fascinated with our ability to reproduce them, because now plate printing was more common, the printing presses were more available. And interestingly enough, there had to, maybe Dave knows the answer, there had to be, I don't know the exact nose count, but there had to be dozens of versions and variations and publications of these constellation star charts. They must have just been flying off the shelves. People like them. We like library books. You know, if you had a library or a sitting room, you'd want to adorn them with one of these huge sky charts. You'd probably also have your amylary sphere out there too. But these were, you know, people of distinction had these big sky charts. So this one, from 1801, now we're 200 years downstream or upstream, I guess downstream, you know, of Bayer's first attempt. And what we're seeing here actually are the constellation figures are more and more embellished at the time when there are more stars. And Johann Bode also incorporated 2,500 of John Herschel's nebulae into this. I mean, this thing is jam-packed. At the same time, we're hiding all this stuff behind the wings, Virgo's wings and gossamer gown. And more and more of these charts wanted to be used for true science and astronomical purposes. I mean, by 1800, serious astronomy was being done. You know, in the mid-17th century, Lord Rosse was over there at his Leviathan and using these star charts, trying to make sense out of them, and he couldn't. So there had to be something done. We had taken this about as far as we could go. And as science progressed, as astronomy became more of a legitimate science, mythology started taking a back seat. So in the mid-1800s, someone named John Dean came along and stripped away all the mythology. All we have now are the stars And as far as I can tell, he kind of invented the idea of tying these stars together with these little stick figures by lines, which still kind of maintain the identity of the original constellation, but removed all of the flotsam and jetsam of the adornment of the constellations. And you can see in Leo here that while the constellation figures are gone, we're back to only the essential stars and their Bayer designations. This is something he could have put additional stars in, but for whatever reason, he was maintaining essentially the same star charts as Bayer had done originally. But this shows that what he's done is strip away everything and come up with these stick figures, which actually we're still using to some extent. I'm using a free software program here. I like the way they illustrate. It's called Charts to Seal, to just illustrate my point here, and from time to time you'll see that. So our modern constellation figures kind of retain all of the outlines that we saw Dean use. It's very rare to pick up a book anymore on constellations and see the mythological figures. Sometimes you'll see an outline, but it's just for the purposes of, I think, tying these constellation figures to the mythology. So this is kind of an area of the sky that we'd probably see if we looked out tonight. Interestingly enough, you know, when we were back in Ptolemy's days, all the way up through fairly recently, we talked about the constellations being the constellations. In other words, the constellation of Orion was the stars that are tied together by the lines in Orion. It came to pass in about 1928, the International Astronomical Union fixed the number of constellations at 88, said that's it. Nobody gets to add their own constellations. People were putting constellations in honor of their patrons or the king. No, you can't put new constellations in the sky. That's it. And actually, if you buy a star and put somebody's name on it and give it to them for Christmas, that's a nice gift, but that's not official. The name will never be on a constellation chart somewhere. In addition to that, we also organized the constellations by boundary markers. And everything inside of those boundary markers, excuse me, I'm going to get something to drink. Thank you. Everything inside those boundary markers is considered to be within the constellation. If we look at Orion, the boundary markers which preserve pretty much the outlines of these constellations. They're all weird shapes because we're trying to accommodate pieces of the constellation. I don't know, if somebody, you know, had invented constellations, I think we would have had to do it ourselves, just because it was important to somehow identify areas of the sky. Ours would probably be some boring grid pattern. This is a lot more interesting. And then eventually, of course, you know, now in the area of remote telescopes and device-aided telescopes, you know, the idea of needing those patterns in the sky to help with star hopping and whatever have lost its meaning. We just plug in the coordinates and we're good to go. So even the outlines themselves, I see in many apps now, tend to be losing their function and popularity. I kind of hate to see those go. But I don't know about you. I've been doing this most of my life. I go out there and I still see those lines between the stars. They're just, oh, I see those lines. Yeah, they're in my head. They're in my brain. And then, of course, someday, someday those lines will probably be gone altogether, and we just won't need to see the boundaries. Our telescopes and device aided don't even care what constellation things are on. Just tell me the RA and the declination, and we're good to go. So to drop back for just a second and kind of trace the history of our understanding of the stars, this is our friend Hipparchus again. And we used to use crude instruments to kind of get a fix on star positions. And he's credited with the first, we saw his work displayed in the catalogs of Ptolemy. And he made the first known measurement regarding parallax in about 189. Oh, here's Cassiopeia, the queen, come in to get her scratches. Okay, Cassie, good girl. We went on to refine our measurements. Again, this is before the invention of the telescope. This is how we were exploring the heavens. Large mural quadrants, which were huge instruments and mounted firmly against walls. We have to understand that instruments like this were only as good as our ability to hold them steady and the precise functionality of how they were built. So these mural quadrants are actually fastened to the wall. I think the most famous one was Tycho Brahe's mural quadrant. And this is interesting because this is a painting on the wall. This is the you can't see me pointing. Can you see a pointer over here? Is this functioning as a pointer? Okay. This is a painting on the wall. This is Tycho sitting in his chair, pointing up through the window. But in reality, this is just a painting on the wall. This is the quadrant, a quadrant being a quarter of a circle. This is an observer, and he's looking through this, and he's reading off the measurements in terms of arc minutes on the subdivided quadrant here. And these are his assistants writing things down. Now, I don't know about his dark adaptation, but I see people with candles. That would have had to been very bright. But this is how Tycho came up with his very precise measurement. He had other things like sextants and quadrants that he was using, but this was his principal weapon of attacking the universe. The sextant was a smaller, this is now a sixth of a circle. The quadrant was a quarter of a circle. And these were also popular. And Johannes Hevelius here and pressed his wife into duty to help him with the measurements. Not long after this, actually, much further into the development of the telescope, we've now hurdled here a couple hundred years. Our fascination in the professional observatories with measuring the stars and the planets. Even though some early work had been done by John Herschel, Lord Rosse, and others, we knew that deep sky objects existed. But we really saw that more, let's just let the amateurs deal with that. And the amateurs had the really big telescopes. And they were already discovering spiral arms and things like that. But the professional observers were studying double stars and the parallax of stars. And that was good work. It was good work. But this is the state of the art. The professional observatories, even though there were people with 48-inch and 70-inch reflecting telescopes out there, the real turn for astronomy was with taking the spectroscope, which had been invented in the early 19th century as a means of determining the color of flames and so forth, were turned onto the sun. And Isaac Newton was familiar with the prism because he used a spectrum, because he used a prism to determine that from the various spectrum of starlight. We started attaching them to telescopes, and that's when we really started knowing about stars. We always knew where stars were, what they did, how they moved. We knew something about their distance. We didn't really know what they were made of, until we were able to determine their spectrum, which revealed to us the composition of the stars, the chemical makeup of the stars, which opened up a huge new field called astrophysics. And George Ellery Hale was not the inventor of astrophysics, but he was a huge, had interest in solar observation. And of course, we know that he was fundamental in getting Yerkes Observatory up and running, and the 102-inch telescopes were George Ellery Hale's brainchilds. So once we were able to dissect the spectrum of the sun, we were seeing chemical properties in the sun that we were seeing right here in flames and things we were familiar with. And we thought, wow, we didn't really know what the sun was made of, but actually it seems to have some of the same properties that we're seeing here on Earth. Not totally, but they started tying things together. And they noticed that not all stars had the same spectrum. So as we were starting to examine the spectrum of stars, we really started getting an idea of what they were made of, which opened up the whole idea of why stars are different colors, because they're larger masses, they're burning more brightly, and they have different spectra than stars like the sun. So just based on it, what is called its spectral class, our sun is a G-type yellow dwarf main sequence star. We wouldn't think it the star is a dwarf star, but there are certainly larger stars. And I'm sorry to say that I believe that part of my PowerPoint bit the dust. I can't show you that. Herschel spent a lot of time under the night sky. He was a musician by trade, but really got hooked on astronomy. And we know him, he's famous for building his own telescopes, and he became what could be said was the world's finest telescope maker. And his telescopes were mainly reflecting telescopes, and he ground his own mirrors and did pioneering work. He was the one that, you're reading this quote from him, he was comparing it to a luxuriant garden. Being a musician, I guess he was also quite a poet. But in my mind, he also bears one additional distinction. We talk about aperture fever. I think victim one must have been William Herschel. He had a good idea here, and he came up with a marvelous aperture 18-inch telescope here, which had a 40-foot focal length, by the way, and you took your life in your hands climbing up there to to look at the prime focus. But as was the case with Lord Rosse's telescope sometime later, they were just too big to be aimed. They weighed tons. The mirror alone could weigh a ton. And they also were very subject to deterioration because they were using metal speculum mirrors. And they had to polish that, and the mirrors deteriorated very quickly. So he kind of left that and went back to his more reliable telescopes, which was, I think, something in the neighborhood of 18 inches. This is a 48-inch aperture. I'm sorry, I think I said 18 inches. His go-to telescope, the one he discovered Uranus with, was an 18-inch telescope. But what he noticed was that these stars are different colors. You know, the human eye isn't very good at determining color of stars, mainly because of that small aperture we have of a 1/4 inch. The larger stars we have some hope for because they are large enough for us to pick up the colors, but the dimmer star colors really aren't picked up too well by our eyes. We often don't perceive the color of those any more than we do the color of deep sky objects, which in many cases are beautiful reds and greens, principally greens. So that's our luxuriant garden. And a star's color tells us an awful lot about it. This is what's known as the main sequence, which means that most stars during their normal lives, and there is some real aberrant behavior out there among stars, but fall into these types of categories, and they're lettered. And, whoops, sorry about that. Let's see, what is this? Oh, be a fine girl or guy, kiss me, is the way we're going to remember that. There'll be a quiz at the end. So they're classified according to their color temperatures. Now here, we've broken them down by color, and we say, does the color tell us anything about the star other than the fact that it's a color? The answer is, colors tell us a lot about how hot the stars are. The bluer to whiter colors are hot. So we run the spectrum of hot to cold. Not cold as cold would be, but cooler. And the M-class stars are the coolest stars. And we'll see a little bit about what else that means. They also tell us a lot about their lifespans. The hotter and bluer the star, the shorter the lifespan. These are blue giants that live a couple 100 million years and are gone. These are like red dwarfs that can live billions of years. There's some theory that these could live trillions of years, and we don't know that we'll ever know the answer to that, since our star is going to end its life in about 10 million years and become a beautiful planetary nebula. So the hotter they are, the shorter they live. Also, the hotter they are, the larger they are. Remember, these are hot nuclear furnaces, and these stars are consuming their hydrogen like, my Uncle Barney at a Pizza Hut. They're just going through that like crazy. Stars like the sun are more conservative. They're smaller mass, and they go through their hydrogen mix in more slow. And of course, here we have these stars that can be billions of years old. This is an interesting one. And these are stars by how many there are in the galaxy, and probably by interpretation of the universe. That is to say, what we can see, the earlier universe that we're hoping to see some of the first stars would have a different percentage. But at any rate, there are very few of these blue supergiants. 1/10. So we go all the way down here and we see there are more of these little guys that are living boring, longer lives than even stars like the sun. So there are 8% of the stars in the galaxy. Only 8% are stars like the sun. And we happen to know that probably it's these stars down here that have the best chance of having planetary systems. These guys don't live long enough. If they start with planets, they blow through them before the planets would be able to develop any type of life.
Hey, Bob, can I ask a question?
Of course.
Michael Cowper is asking, where did these letter designations come from? The star designations?
Yeah, that's an interesting question, Michael. They probably generated someone at Harvard Observatory, when Pickering was in charge there and they were cataloging all the stars in the sky. I don't know the answer to that, actually. They seem rather arbitrary. I've read an article about that, but I'm just not remembering. Maybe somebody can do a Google search on that and get back to us. But I'm afraid I don't know the answer to that.
Don Gavzik is saying that Annie Jump Cannon, I think she was at Harvard, right?
Oh, absolutely.
Camp with the first ones.
Yeah, she was with Henrietta Leavitt and some of those computers, the women that were hired to be computers. All right. Any other questions, Suresh? Okay. Let's just move on here to some specific things. Star Arcturus, which we saw earlier is the alpha star in the constellation Boötes, is the fourth brightest star in the sky. Generally, the brighter the star, the more designations it has. So let's talk a little bit about Arcturus. Arcturus is famous for many reasons, but the one that I think is the most interesting is what I'm going to tell you about. So from the Chicago Tribune is a story that every star has a story, but this is a curious one because the star Arcturus has an electrifying story in relation to the 1933 World's Fair. Okay, not even I was alive in 1933, so I don't remember this, but the story is really interesting. 1933, the Chicago World's Fair was a century of progress exposition, and it was exactly 40 years after the last great fair in 1893. Edwin Frost, the ex-director of Yerkes Observatory, hit upon a bright idea, pun intended, to kick off the fair with a flare. At that time, the star Arcturus was thought to be 40 light years distant. We now know that it's 37, but at that time, it was 40. So on this 40th anniversary, I came upon the idea of using light from the star Arcturus to turn the lights on at the fair. So a general electric photoelectric relay and photo cell setup was set up at Yerkes Observatory. So the idea was the light from Arcturus was going to be focused on this photocell and be the switch to turn on these lights at the opening ceremony. There were several other observatories positioned around the country because being in Williams Bay, Wisconsin, I assume most of you know where that is. I had an opportunity to tour Yerkes before it was mothballed. They were also ready to back up Yerkes in case they got clouded out, but they didn't. That was a big hit. And the Chicago, by the way, of course, Yerkes was operated by the University of Chicago, so they had a hand in this. Could a more perfect marriage of poetry and science ever be arranged? We marvel at the promoters and astronomers for conceiving this ingenious way of linking the past and present. So that's a bit of the story about how Arcturus achieved its fame and fortune. Excuse me.
So Bob, as you're getting some water, the point about that is if Arcturus is 40 light years away at the time, the previous World's Fair in Chicago was in 1893, which was 40 years prior.
That's right. And that's why they thought the 40 light years for Arcturus was a good idea. They didn't know it was 37 light years. We didn't find that out till later. So the common name of Arcturus means guardian of the bear. Why would they call it the guardian of the bear? Interestingly enough, Boötes and Ursa Major sit next to each other in the night sky. And there's also a little saying that says, arc to Arcturus. So if you come off the handle of the dipper, you meet up with Arcturus. Excuse me. Most stars up to about third magnitude have common names. So there are hundreds, but only a few dozen are named. Names of the brightest stars are in popular use. So Arcturus also has a Bio-Greek letter, which is Alpha Boötes. It also has the Flamsteed number of 16. Yeah, I don't know what we do when I start losing my voice. being in quarantine as long as I haven't much practice talking. So here's Orion in the night sky. And let's talk about a few things. Betelgeuse is in the the right shoulder of the giant, and it's called Alpha Orionis. Plamsteed number 58. And the term Orionis is a genitive form of Orion, meaning the alpha star of Orion, a possessive form. Rigel, the left leg of the giant, is Beta Orionis, with a Flamsteed number of 19. Sorry, gang.
Hey, Bob. Given a time check, we're at 3 o'clock right now.
Okay.
Why don't we, how much longer do you think? Maybe 10 minutes or so?
I'd say my voice has about 30 seconds left, yes.
Do you want to stop here and take questions, or you want to go for 4 minutes?
I've got considerable more content here. This would be a pretty appropriate place to stop, yes.
Okay. Well, we could always put the rest of your presentation into it.
I owe you guys about 45 minutes. That I messed around with my slides, and so hopefully your next virtual meeting will go better.
So
But
while
yes,
we're coming up with questions,
sure.
a couple comments that I see. One from Ron Schmidt. Pickering actually assigned the spectral type a letter of the alphabet based on the strength of the star's hydrogen, with A being the strongest. And then Michael Cowper said the Vikings called Arcturus the day star because keen-eyed people could see it during the day.
Oh, that's a good point. Yeah, I sure want to point out that we're going here on Middle East constellation designations. You know, every culture had their own lores and myths about these stars. That's true of the Chinese that were observers, as well as, you know, the other cultures. So I'm glad you pointed that out.
So let's take some questions. Does everybody have any questions about anything that's been spoken so far? Did we answer everybody's questions already, maybe?
No other questions?
On the call. Okay, well, if there are no other questions.
Well, I want to thank everybody for your patience and your tolerance. I did put a considerable amount of work into this, but we must have had a hit of some kind here that really got this screwed up. So there's a lesson to be learned here somewhere, and when you find out what that is, be sure to let me know.
Oh, you did great, Bob. I think everybody learned a lot from the presentation.
Well, perhaps sometime we can come back and have part 2. I'd like that.
Yeah, we could definitely.
Appreciate everybody's attention today. Very much appreciate it.
All right, everybody, if there's no other questions, I think we'll end it here. Thank you guys for coming. The next presentation will be on January 23rd. Mike Shaw, who's, if people know Mike is a phenomenal landscape imaging amateur astronomer. He actually runs courses on this topic. He's going to do a presentation for us on how to take pictures with landscape, with objects in the foreground. Like, say you go to a state park and you take a picture with, trees in the way or mountains or what have you. He's wonderful at this. So that'll be at 1 o'clock on Saturday, January 23rd. And I'll communicate more about that as we get closer. So I want to thank Bob for everything he did and getting through with his cough and everything. Really appreciate it. This is the first virtual presentation we've done, and I think it worked great. So, Vols, if you're still recording, you can stop the recording now.